What do a swaying bridge and a fluttering airplane wing have in common? They might seem totally unrelated, but they're actually governed by the same hidden set of rules. So welcome. This is our deep dive into nonlinear dynamics, where we're going to start unpacking the complex and, often unruly systems that really shape our world.
So let's ask the big questions right off the bat. Why does a bridge sway? How does a heart keep its steady beat? What really causes a market to crash? These things feel so different, but they all share a hidden language, and that is the language of nonlinear dynamics. In this series, we're going to learn how to speak it.
But, before we can run, we got to learn to walk. So to really get a grip on the beautifully complex and wild nature of the real world, we first need to master the simple, kind of idealized world of what we call linear systems.
Okay, so think of linear systems as the straight-A students of physics. They follow the rules perfectly. Everything is perfectly proportional. You double the force on a spring, guess what? It stretches twice as far. The math is clean, the behavior is totally predictable. It's a beautifully tidy, predictable world.
And here is that tidy world in action. What we're looking at is a classic mass spring system. You give it a push, and it just oscillates in this perfect, repeating rhythm. That picture on the right, the phase portrait, that's just a map of the system's position versus its velocity. And as you can see, it traces a perfect circle. It never does anything weird or unexpected. It is the definition of stable.
So it's simple, it's predictable. But as you and I both know, the real world is, it's rarely that well-behaved. This whole neat linear picture is really just an approximation. It's a starting point. So what happens when systems start to break the rules?
And that brings us to the really interesting part of our story. What happens when systems disobey? This is where things get messy, unpredictable, and frankly, infinitely more fascinating. This is the nonlinear reveal.
And the difference is it's like night and day. In the nonlinear world, all those neat rules we just talked about, they fall apart. The output is no longer proportional to the input. The bedrock principle of superposition, the idea you can just add two solutions together to get a third, that completely fails. Forget about finding exact perfect solutions. Instead, what you get is complex, surprising behavior that linear math simply cannot predict.
Now check this out. This is the van der Pol oscillator, a very famous nonlinear system. It doesn't matter if you give it a tiny little nudge or a massive push. See how both of those starting paths eventually spiral into the exact same self-sustaining oscillation? A linear system could never, ever do this. It's a fundamentally nonlinear thing.
And that beautiful, stable pattern we just saw, it has a name, a limit cycle. It's a signature of a nonlinear system. It's an oscillation that the system wants to be in. It just naturally settles into this rhythm all by itself.
So the really crucial idea here is that a limit cycle is like a magnet. It's a closed loop that attracts all the nearby trajectories. And its size, its amplitude doesn't depend on how the system started. That's a huge idea. The system has its own preferred rhythm it will always return to. And we see them everywhere, from the beating of our own hearts to the dangerous flutter of an airplane's wing. Understanding these is not just some academic exercise, it's absolutely critical engineering.
That limit cycle is more than just a cool pattern. It's a clue. It's telling us that nonlinearity isn't just some mathematical curiosity, it actually represents the true rules of reality. So let's zoom out and just ask, what is nonlinearity really?
Well, as this quote from our source material puts it pretty bluntly, it's not easy. The math you need to describe this kind of behavior is just fundamentally harder. The nice, neat, cool box we have for linear systems, it just doesn't work here.
But here's the cool part. That challenge has led to some incredible innovation. Because those exact, clean solutions are so rare, researchers have developed an entire arsenal of powerful, really creative methods to find approximate solutions that get us incredibly close to the real thing. And just look at the variety of tools in this toolkit. Perturbation methods, homotopy methods, harmonic balance, the list goes on and on. Each of these is like a different lens, a different tool for peering into the complex dynamics of a nonlinear system. And don't worry, we're going to be unpacking a lot of these throughout this series. But nonlinearity isn't just about stable patterns like limit cycles. Sometimes it can lead to something far stranger, far more complex. So let's get a little glimpse into the world of chaos. Now, we use the word chaos all the time to just mean random or messy, but in dynamics, it has a very precise meaning. It's behavior that is totally deterministic. It follows exact rules, but it's so sensitive to where it starts that it appears random and is impossible to predict in the long term. This is chaos.
What you're seeing is the path of a Duffing oscillator. The system's path just weaves and folds over itself, exploring this beautiful, intricate structure. But here's the mind-bending part. It will never repeat the same path twice, ever. And yet, it's not random. It's confined to this beautifully well-defined shape, which is known as a strange attractor.
And the equation that generates this astonishing complexity? Well, it's deceptively simple. The Duffing oscillator is really just a basic mass spring system with one little extra term, a cubic nonlinearity. That tiny change is enough to unlock this entire universe of rich, chaotic behavior. It's the classic example of how simple rules can generate infinite complexity.
Okay, wow. We've seen linear systems, we've seen limit cycles, we've even dipped our toes into chaos. It's a lot to take in. So you might be wondering, where do we possibly go from here? Well, this slide lays out the roadmap for our entire series. It's your guide to mastering all these concepts.
You know, the core idea is simple. The world is nonlinear. And our goal throughout this series isn't just to learn a bunch of equations. It's to learn the rules of reality so we can do things like build safer bridges, design more reliable pacemakers, and create truly innovative technology. So here's our training program broken into 5 key steps. First, we'll master the fundamentals, things like phase plane analysis and stability. Second, we're going to build our analytical toolkit with techniques like perturbation methods. Third, we'll dive into the computational world to really explore things like bifurcations and chaos. Fourth, and this is the really cool part, we'll apply everything to real-world problems. And finally, we'll learn how to not just understand, but actually tame these complex systems with nonlinear control.
And the applications are what make this stuff so powerful. We're going to use these tools to understand how to control vibrations in massive structures like bridges. We'll explore how nonlinearity can actually be used to harvest energy from seemingly random motion. We'll even see how it governs how waves move through next-generation metamaterials. This is theory put directly into practice.
So that's our journey, from the simple, predictable straight line to the intricate, chaotic dance of reality itself. The world is nonlinear. The only question is, are you ready to learn its rules? Join us for our next explainer, where we'll dive deep into phase plane analysis. See you there.